Hi, my name is Jenny Kane, and I am the Sales Manager at H2 Laboratories. Welcome everyone to this webinar put on by the SPWLA. Today we will be discussing our accurate porosity measurement done on cutting samples using NMR developed by Green Imaging Technologies and H2 Labs. For some background on our companies, Green Imaging Technologies is the industry leader in NMR rock core analysis. Our software is the backbone of the GeoSpec line of NMR rock core analyzers, which are used by all major oil producers, oil service companies, and the most active research institutes worldwide. For those that don't have their own lab or service companies who want to add NMR to their product offerings, H2 Labs, a subsidiary of Green Imaging, leverages our expertise and patent technologies to offer NMR rock core analysis services both directly to customers and via industry partners. Our team of experts are completely focused on rock core analysis and as such have developed relationships with the most respected researchers and experts in the NMR rock core analysis field. Speaking of our team, I'm happy to introduce Dr. Michael Dick, who is a senior research scientist at Green Imaging Technologies, who will be giving our talk today. Mike got his master's degree in science from the University of New Brunswick, where his postgraduate work focused on molecular physics. He then received his PhD from Waterloo University. After graduating, he worked in astrophysics with NASA's prestigious research arm, the Jet Propulsion Lab in California, before taking a nuclear physics position at Bubble Technology Industries, working at the Chalk River Nuclear Facility. At BTI, Mike developed unique radiation detectors that have been deployed in a variety of applications, including defense, homeland security, first responders, space agencies, standards groups, and research institutions. Here at GIT and H2 Labs, Mike has led the research efforts on a variety of applications using nuclear magnetic resonance to measure various petrophysical parameters on rocks. Most recently, Mike has been leading the research on a novel new measurement of porosity in cuttings. So without further interruptions, here's Mike.
All right, thanks, Jenny. So with the global pandemic still ongoing, we as research scientists have been missing out on our regular opportunities to get together and share our results. So I was really excited when the SPWLA presented this opportunity to present a webinar on some of our most recent work we've been doing on determining the porosity of cuttings. So let's get started. So as Jenny said, we at H2 Labs specialize in NMR core analysis. Probably the most important measurement we do is determining the porosity of core plugs. To do this, we measure the transverse relaxation time of the fluid inside the pores. And the rate of the transverse relaxation time is governed by this equation right here. And the transverse relaxation time of the bulk fluid is usually large, so this term can usually be neglected. So this means that the rate of transverse relaxation time is proportional to the surface to volume ratio of the pore. And what this means is that small pores with large surface to volume ratios have fast decay, whereas large pores with small surface to volume ratios have slow decay. What we measure is actually the sum of all the transverse relaxation times decays in all the pores. We get an overall decay that we fit to an exponential function. We then invert that function to get a T2 distribution. And as I said, because T2 is proportional to surface to volume ratio, this is essentially the pore size distribution for the core plug. And we then calibrate our instrument so that the y-axis of our plot here is proportional to equivalent water volume, which means the sum of the area under the curve gives you the pore volume of the rock. So then if you want to know the porosity, you just take the pore volume and divide it by the bulk volume of the plug, which is easy to measure by measuring its length and its diameter. Of course, this is easy for core plugs, but as you'll see, it's not so easy to measure the bulk volume for crushed up cuttings. So this has been the majority of our work, is figuring out what's the best way to measure the bulk volume and the pore volume of cuttings. So first of all, why are we even interested in measuring the porosity of cuttings via NMR? Well, first of all, conventional methods for determining porosity of cuttings do not give immediate feedback of the porosity while drilling, are complex, expensive, and prone to error. Can't be used on modern drill cuttings, which were drilled with with bits such as PDC, which are too small. But NMR measurements should be well suited to determine the porosity of these drill cuttings efficiently and accurately. So the goal of this work has been to develop a procedure for measuring the porosity of cuttings via NMR in real time in the field. So first of all, as I said, measuring the bulk volume of cuttings isn't easy. So we came up with a procedure where instead of measuring the bulk volume of the cuttings directly, we measure 3 other measurements that are easy to measure with NMR. V total, V cuttings plus fluid, and then V cuttings alone, which is essentially the pore volume of the cuttings. And when you do you subtract these two and add the pore volume, you end up with the bulk volume. These 3 measurements are easy to do. They're carried out in a NMR invisible Teflon vial. They take between a few minutes and a few seconds to do. But as you'll see, accurately determining the pore volume of the cuttings has its own challenges. I'm going to spend the next couple of slides delving deeper into this equation right here and then you get a better feeling for why it is so hard to measure the pore volume of the cuttings directly. And hence, if you have trouble measuring the pore volume of the cuttings, you're also going to have trouble measuring the bulk volume of the cuttings. So first of all, the NMR measurement will measure the fluid inside your NMR tube. So if you wanted to know the bulk volume of this cylinder here, you'd first have to measure the bulk volume of your NMR tube. You then put the cylinder inside the NMR tube and you measure the bulk volume of all the liquid around the tube. And then of course, if you subtract the two, you get the bulk volume of the tube. That works as long as there's no fluid inside the cylinder itself. Now, if there is fluid inside the cylinder, of course, you're going to underestimate the bulk volume of your fluid. So in order to account for that, you have to do a third measurement, which is to measure the fluid inside the cylinder directly. And then if you add that back onto this equation, you end up with the right bulk volume of the cylinder. So how does this apply to core plugs? So it's the same thing in core plugs. So you still, if you wanted to know the bulk volume of the core plug, you'd have to do these 3 measurements. Luckily, we're experts, as I said, at measuring the pore volume of core plugs. So if you wanted to know the bulk volume of the plug, you'd do these 3 measurements. But of course, that's ridiculous. Why would you ever measure the bulk volume of a core plug in this way? You're much more likely to measure its diameter with a pair of calipers and its length with a pair of calipers and calculate its bulk volume. But that's not the case with cuttings. You can't just get out the calipers and measure the bulk volume. So you have to do these 3 measurements in order to get the proper bulk volume of the cutting. So this explains why we need to do this procedure. The problem with this procedure is it seems easy on paper, but the problem is what'll happen is if there's any surface fluid remaining on the cuttings when you go and you measure your pore volume of the cuttings, you're going to overestimate your porosity in this equation right here. And why does the cuttings have surface water on them? Well, when you go to saturate them, they acquire surface water, and then if you don't eliminate that surface water, you're going to end up overestimating the cuttings. So that's been the crux of this work, is how do we account for this surface water so that we can apply this equation correctly. I'm going to give you a couple of examples of why surface water does interfere with the T2 measurement and the pore size distribution, and hence our determination of porosity. So here you go. Here's a cartoon showing why surface water is so important to our measurements and why it can hamper our measurements. So first of all, you can see that it's possible for the surface fluid to overlap the T2 distribution of the water in the pores. Or in other words, the water on the surface can have a T2 at a similar value as the water in the pores. And the other thing is, as the cuttings get smaller and the surface area becomes larger, that effect of the surface fluid can become very important. And in fact, here's a cartoon where your surface fluid is larger than your pore volume here. So here's a real example of this. So the red trace is the pore size distribution for this plug here. The blue trace is the pore size distribution for these cuttings here that have been saturated. We did make some effort to eliminate much surface water as we could here by patting them dry with paper towel. And in addition, this is the T2 distribution for bulk water. So clearly, we have a big surface water problem here. And if we used all of this T2 distribution to calculate the porosity of these cuttings, you'd get 30%, 30 PUs, which is 3 times higher than the expected value from the core plug. And clearly, you'd never do this. That's ridiculous. What you'd more likely do is apply a T2 cutoff. And in this case, you might apply a T2 cutoff right around 250 milliseconds, and that where it logically makes sense. And then you'd say everything above 250 milliseconds is due to surface water, and everything below is in the pores of the cuttings. But the problem with T2 cutoffs is it's hard to accurately determine where to put them consistently. Even in this case, where you might say this is pretty obvious, you're still gonna, if you applied the cutoff here and only included this area here to calculate porosity, you're going to be 3 PUs below the expected value. And sometimes you can use a plug data to help guide your positioning of T2 cutoffs, but that defeats the purpose of this measurement. We're trying to develop a measurement where we only need cuttings to determine the porosity of the samples we're looking at. Just to emphasize here one more time, this is actually a best case scenario. This is a case where there is some separation between surface water and water in the pores. And as I'm going to show you, that's often not the case. Here's an example where that isn't the case. The black trace here, black T2 distribution, is the T2 distribution for this core plug right here. Whereas the green is the T2 distribution for the cuttings. Now the cuttings have been saturated, and we made some effort to eliminate some of the surface water off of them by spinning them in a centrifuge. But clearly a centrifuge didn't get rid of all the surface water. We still have way too much signal, way more signal than what we would expect. And if you used all the area under the green to calculate the porosity of the cuttings, you get 24 PUs, which is about over 2 times higher than what it should be based on the core data. And if you didn't have any knowledge of the T2 distribution of the plug, you might apply a T2 cutoff right here around 50 milliseconds. And again, you'd say everything above the cutoff is due to surface water and everything below is due to water in the pores. But even if you did that, you're still going to be about 2 times higher than the expected porosity. So that's not good. Now, if you did have some information on the core plug, from the core plug, you would apply a cutoff right here, and then you'd arrive at the right porosity from the cutoff T2 green cutoff T2 distribution. But the problem with this is there's no physical justification for applying the cutoff here. The T2 distribution that you end up with after you've cut it off doesn't look anything like the expected T2 distribution from black. And in addition, I needed core plug data to calibrate the cutoff. So that defeats the purpose of this measurement. We're trying to figure out how to do this without core plug data. So obviously, in order to get our method for determining porosity using NMR to work, we need to deal with the surface fluid. So initial testing, we used a crushed core plug as a surrogate for real cuttings. And the reason we did this is because we knew the porosity of the plug, and then we could determine whether or not, when we run it through one of our proposed procedures to eliminate porosity, to eliminate surface water, whether or not we were getting the right porosity. And we tried out a whole host of things, including paper towel drying, screening them, rinsing and washing with D2O, centrifuging, applying a surfactant, doping the water, and sonication. And in the end, it looked like centrifugation was the best option for eliminating the water from the surface of the cuttings, or the surface of the crushed samples in this case. We summarized all this data at the 2017 Society of Core Analysts meeting, and if you're interested in more details on this work, feel free to read our paper. But just to quickly summarize is essentially, if you're going to spin these cuttings, what you're essentially doing is spinning them and spinning the water off of the surface. Now the problem with this is if you spin them hard enough, you may eliminate the water from inside the pore. So we wanted to make sure we weren't doing that. So we ran a couple of experiments, one on a sandstone sample and one on a shale sample, where we looked at the detected volume versus centrifuge speed. And in both cases, the detected volume dropped quickly at low centrifuge speed and then leveled off after that. This corresponded to eliminating the surface water at low speeds, followed by the elimination of pore volume. And we know that it levels off right near the volume levels off right near the correct porosity for each of these samples. So this was showing that, yes, as long as you could spin the samples pretty hard and not eliminate much of the pore volume. This makes sense because if you look at the capillary pressure equation shown here, it says that if, in order to overcome the capillary pressure, by spinning, where we need the difference between the inlet and outlet face to be quite large. We need this turn to be large, and that's not the case for samples, crushed up samples, which will have short, capillary lengths essentially. So it's not unreasonable that you can't really spin the water out of the pores. Anyway, using this technique, centrifugation, we were able to determine the porosity of crushed core samples to within 6% of their expected value. That was great. And that's where our work stood for a long time. It worked well on crushed samples, but we yet to test it on real samples from a real well drilled with an actual drill bit. But recently we ramped up work again, and we began looking at real cuttings rather than crushed core. And what we quickly realized is that real cuttings are crushed by the drill bit to much smaller sizes than we'd been crushing our samples to. And the other thing, we ran it through our centrifugation procedure, and we quickly arrived at the wrong answer. We weren't getting the right answer. We were getting answers that were porosities that were too high. So clearly we needed to go back to the drawing board, and we needed to look at this problem of surface water again. And to do this, we began by sieving real cutting samples to different size, and began to explore the effect of sample size, cutting size on porosity determination. And the next slide talks all about this. So here on the left, you can see different cuttings sieved to different sizes. And so starting with the chunked sample, we ran it through our procedure, and we determined that in this case we didn't need centrifugation. We dried them with paper towel. We run it through our procedure, and plotted in black here is the pore size distribution you end up with. And it's really close to the expected porosity of 6.7. We got 6.6 with our porosity. So that's great. But now let's start talking about what happens when we use actual cuttings and begin to run them through our procedure. So if we use cuttings between 1/12 and 1/30 of an inch, we spin them at 3,000 RPM, you get pretty close to the right answer, 7.7 PU versus 6.6 PU. So a little high, but pretty close. But when you get down even smaller, down to 1/70th to 1/30th of an inch, you spin them at 3,000. Now you're almost a factor of 2 too high. That's plotted in blue right here. And then if you get less than 1/70th of an inch, and even if you spin them at 3,000, you're way up here in green, and you're over almost three times the porosity that you expect. And even if you spin them faster at 5,000, 7,500 RPM, you don't get back to the original porosity. You're not eliminating all the surface water with centrifuging. So clearly, centrifuging alone and our original technique we developed wasn't going to work. We had to go back to the drawing board. Excuse me. So we went back to what we had been trying before, and we tried all these things again, but this time we tried combinations of things. And what we eventually settled on was that a combination of D2O rinsing and centrifuging eliminated the signal from the surface fluid, from the fluid on the surface of the cuttings. And the reason for this is that D2O replaces the water on the surface of the cuttings. And this replacement is effective because D2O has no NMR signal. So when it replaces the water, it's replacing it with something that won't have any NMR signal. So we're eliminating the surface water. And to further test the validity of this method of a combination of D2O rinsing and centrifuging, here's some data. So we got 6 core plugs from same well as some cuttings at similar depths. And we measured the porosity of these core plugs using our standard NMR procedures. And the average porosity of the 6 core plugs is plotted here in red. And then one standard deviation plus or minus is plotted in these black lines here. We then took the cuttings, and first we just spun them in air and used our old technique, and we arrived at a porosity that was much higher than the expected porosity. But then we rinsed them with D2O, and bang, we got right on the correct answer. But we weren't confident enough there. We repeated this rinsing 2 more times because we wanted to prove to ourselves that if you continued to rinse them with D2O, you wouldn't rinse all the fluid out of the pores. You'd only replace the fluid on the surface of the pores. And it clearly didn't. We then tried combinations of higher centrifuge speed and more D2O rinses, and no matter what we did, we never dropped much below the expected value. So this is great. We had real confidence that our technique was going to work. So now we wanted to expand our test base. So that's what we did. So with the help of Epoch Consulting, who provided us with a set of core plugs and cuttings from the same well at similar depths, we were able to do this. So the cuttings were acquired from 10-foot spans in depth, while the plugs were acquired within these spans. The porosity derived from our procedure for the cuttings, as you can see from this 1-to-1 line here, agreed well with the expected porosity from the plug. It's quite good. And any difference in porosity between the plug and the cuttings could be attributed to inhomogeneity in the field, and the fact that the cuttings provide an average porosity over the range of depths, while the core plugs provide a single porosity at a fixed depth. This was a great first, pretty bit larger data set. It looked pretty good. So next, we wanted to expand our test space even further. So we partnered with Premier Oilfield Group, and they provided us a set of 47 samples, all taken from the same well. Each cuttings was taken from a 10-foot depth span. In addition, they provide us with 6 core plugs from the same well at different depths. They had also previously tested the porosity of those plugs so that we were able to compare to their previous results. We also crushed a portion of each of these plugs so that we could further verify our method on crushed samples in addition to real cuttings. So the porosity of the plugs was determined, as I said, with standard NMR NMR techniques, while the porosity of the cuttings and the pseudo cuttings was determined using our procedure. In addition, the well had an NMR log completed on it, so there was a lot of information on this well that allowed for excellent verification of our method. So this is the first plot of the NMR log versus depth for the first section of the well that we looked at, from 10,750 feet deep to 11,100 feet deep. So the blue trace here is the NMR log taken in 6-inch increments in depth, whereas the red trace is the NMR log taken at 10-foot averages. The green dots are our measurements of the cuttings. The black dots are our measurement of the plugs. Pink dots are the measurements of the plugs done by Premier, and the blue dots are our measurements of crushed core samples using our technique. So the first thing to notice is our measurements of the plugs and their Premier's measurements of plugs agree quite well. The next thing to notice is that the measurements of the plugs and the pseudo cuttings agree quite well. There was only one pseudo cutting or crushed core sample that it was out by more than 1 PU from the expected value from the plug. But finally, the most important thing to notice here is our green cuttings measurements agree pretty well with the log, which was good. And there's less variance in the porosity than there are in the plugs. And this is as expected because the cuttings are an average porosity over a depth span, whereas the plugs are only the measurement at one specific depth. So here's another range of log that we looked at, from 11,350 feet to 11,650 feet. Again, the red and the blue are the NMR log data, and the green data is our cuttings, and the pink is the plugs as measured by Premier. And again, our data, our cuttings data agrees pretty well with the plug, so we're pretty happy. So this work has been great to work with Premier, and we're going to continue to work with them. In fact, we're in the process of measuring cuttings from another well. That's ongoing as we speak. But beyond just looking at porosity, with such a large data set, we can do make a lot of other interesting comparisons. So the first thing we can do is we can look at how do the T2 distributions compare to a plug data versus cuttings data. And in a perfect world, if our method is working properly, the T2 distribution you get from the plug should be very similar to what you get from the cuttings. So to do that, to make that comparison, we took the plug data from one plug and we compared it to cuttings at a similar depth and cuttings at a similar porosity. So here are those T2 distributions. So the one on the left shows the plug data in black compared with the cuttings data in brown for cuttings of a similar porosity. And you can see that, in fact, It's excellent agreement. It's so close, in fact, you can hardly see the black plug data underneath the brown cuttings data. Over here on the right is the cuttings, the plug data, T2 distribution compared with cuttings from similar depth. And it's not as good agreement, but it's close. And it's not unexpected to see that they shouldn't always agree due to inhomogeneity in the field. What we could say about both of these comparisons, the brown versus black, is they agree a lot closer than the green and the black do. Now, if you remember from the beginning of my talk, the green is the pore size distribution we got when we didn't make a whole lot of effort to remove the surface water. We simply spun it with centrifuge. We spun it in centrifuge. We didn't use any D2O rinsing. Clearly, we've done a much better job eliminating the surface water here. And finally, maybe most importantly, what you can tell from these T2 distributions is that the bit is not destroying the pore network of these unconventional samples we've been looking at. I know people often wonder, is the bit grinding the rock beyond the pore size distribution? And the answer is, at least for the samples we've looked at, no. The T2 distributions are intact. I mean, this excellent agreement is proof of that. So that's great. That's real confidence that our method is working and that the porosity we determine from these cuttings is valid. So moving beyond porosity and T2 distributions, we can talk about the repeatability of our measurements. This large data set we got with the Premier's well gives us a chance to look at repeatability of our measurements. So here's 3 measurements done on 6 different samples. Now, each of these samples was tested for each measurement. The same sample was tested 3 times, and it was dried in between runs and resaturated. And you can see, for the most part, the repeatability of our measurements about 1 PU. But the repeatability might be biased by measuring the same sample multiple times. You might be damaging the sample after multiple measurements, and that could lead to a slight downward trend, which you kind of see here in the observed porosity. And this isn't really a realistic demonstration of the repeatability of our test of what would go on in the field. What's more likely is that you would test the same sample you are unlikely to test the same sample multiple times in the field. More likely, you conduct multiple measurements on cuttings from the same depth. And that's what we did next, and that's what I show on this slide. So here you go. Now, there's 4 samples, and what I mean by 4 samples is these were 4 different cuttings at 4 different depths, and then each measurement was taken on a virgin set of cuttings from that particular depth. So this is more realistic on what you would do in the field. In addition, each of these measurements was done by a different technician. So this data also gives you a feeling for how person-to-person variability of our measurement, what it's like. And you see, despite all this variability, different samples, different people, our variability still remains about 1 PU, which we think is pretty good. But what's more interesting maybe than the variability in our measurement and the variability of the porosity is what's the variability in the T2 distributions that underlie these porosity determinations. So here you go. For samples 2 and 4, these are the T2 distributions, or the pore size distributions for the cuttings that from which these porosities were determined. And you can see that the T2 distributions, for the most part, agree really well. So this means that 3 different samples at 2 different depths, recorded by 3 different technicians, and we still get similar T2 distributions repeatedly every time we make the measurements. This is excellent. And finally, I'd just like to emphasize that because we're so confident that we're getting the right T2 distributions here, that we could go beyond simply measuring the porosity of cuttings eventually. We could actually apply any of our NMR measurements to cuttings. So for example, here's a T1, T2 map that we recorded on some cuttings. And so this can easily be done on any cuttings, and you can use this for fluid typing. So what I'm saying is this technique of porosity determination of cuttings unlocks a whole new world of possible NMR measurements that can be done on cuttings. So in summary, we have successfully developed a method for determining the porosity of cuttings via NMR. The method relies on removing surface fluid from the cuttings rather than a T2 cutoff. This can be performed on both fresh and old cuttings. To date, we've tested over 60 samples from many different unconventional reservoirs, including Utica, Marcellus, Woodford, etc. Samples should, when they come to us, should be washed, i.e. free of drilling mud. We only need 0.5 to 3 grams a sample. The measurements take about 10 minutes to complete. This includes all centrifuging, rinsing, and NMR measurements. And it can work down to samples down to 1/70th of an inch in size. So I'd like to thank everybody for your attention. And if you have any interest in having some cuttings analyzed, please contact us at H2 Laboratories. And I'm now interested in taking any questions you might have. Thank you very much.